my lecture today. Before I get started today, because we are moving very close to midterm one, so by latest Wednesday, I'm actually going to upload midterm one practice questions, and of course, a class will be dedicated, to that. So by next week, I'm actually going to walk you through some practice question, but this week I'm actually going to publish practice questions. Okay, so I want to welcome you to my lecture today. We are still on chapter 8 of the textbook, and we're going to be focusing on interval estimator. Of course, in the outline, I'm actually going to have a recap on point estimator. Then we're going to have a review on error in estimation. Then from there, we're going to go into interval estimator. So let's get started. Um, I want to have a recap on point estimator because the understanding of point estimator is actually needed in interval estimator. And of course, by point estimator, it means we actually make a suggestion about a particular method or formula that we want to use to figure out the unknown value of a parameter, when working with sample. And of course, a point estimator is just going to give a single result, a single value. Okay. And of course, I walk you through some properties of point estimator. We consider a situation where, point estimator could be unbiased or could be biased. And of course, you know how to investigate all of that. So when it is unbiased, if I really want to tell how reliable is an unbiased estimator, of course, I need the variance. And of course, if I want to tell how good is, a bias estimator, I actually need the mean square error. And of course, we use the knowledge of empirical rule and Shepshev rule, to actually investigate the convergence of a point estimator to the true value of a parameter. I remember the other time using the idea of Shepshev, the Shepshev can actually be used to figure out the probability of a point estimator converging to a parameter within a threshold. And of course, if the probability distribution of the estimator is not normal, we can actually use Shepshev rule. But what if in a situation whereby the estimator, the distribution is normal? The distribution of estimator can be normal, either it is normal from the beginning or it is normal after taking a large sample size, using the idea of law of large number. So if it is normal, we can use the idea of empirical rule. And of course, I told you the other time, the central limit theorem facilitate normality, and normality, on the other hand, facilitate standardization and z-score. So when a point estimator is normal, that will facilitate, very easy computation of probability around the point estimator. So we got choice on that. Okay, now from there we move to error in estimation. Let me tell you, whenever we estimate, because we can only estimate working with sample, the only way to get the true value of a parameter is when you work with the entire population. We are limited by budget. We do not have resources for that. We're always going to take a sample. And the moment you take a sample, you're actually going to estimate. And let me tell you this. estimation always come with a cost, and that cost is the error. There's always going to be error. That is not surprising because I told you from day one, model is not the same as reality. Okay, I told you from day one. Now, if model cannot be the same as reality, we don't expect our estimator to be the same as parameter. They're not going to be exactly the same. We're only seeking convergence of the estimator to the population parameter value within a threshold. There's always going to be a threshold. Does that make sense? Okay, so error, of course, and what is the significance of error in estimation? The significance of error is that we're actually going to have opportunity to be able to tell how good is our model, how good is our estimator. Because without error, there's no way we're going to say, how good. So which means, and that is the reason why uh, all statistical models have assumptions. All statistical models that revolve around the error term have assumptions. Assumptions revolve around the error. If I want to tell how good is my model, how fantastic is my model, then I need to be able to revisit whether assumptions underlying the use of the error are met. Okay, and that is the reason why error in estimation is very, very important, because it's actually going to tell us how we can evaluate our model. Now, into today's lecture, and we want to start with example 3. In example 3, as you can see here, we're working with two groups. A comparison of the durability, okay, of two types of automobile tires was obtained, okay, by road, okay, testing samples of N1 equal to N200 tires of each type. The sample size is 100. Okay, we got two types of that. That makes it two different groups, two different populations. The numbers of miles until wear out was recorded, where wear out was defined as the numbers of miles until the amount of remaining tread reached a pre-specified small value. The measurements for the two tires, were obtained independently. Okay, and the following means and variances were computed. Now, when you take a look at what we have here, the Y bar 1, the Y bar 2, and the sample means, okay, they will obtain this and the variances using the 100 tiles for each category. Now, what is the question? Take a look at the question right now. Now, the question, say estimate the difference in mean miles to wear out and place a two standard error bound on the error of estimation. Okay, because we're working with sample, we're always going to have error of estimation, and of course we're always going to place a bound. Does that make sense? We're always going to place a bound. Now we are asked to place a two bound on the error of estimation. Now, when you take a look at this, the true value of a parameter, we are actually looking at the difference between the two population mean, but because we do not have access to every item, like here now, all tires, we're only using 100 of them, we're actually going to have a consider point estimator for that. And the point estimator, okay, is actually this guy here. The point estimator, okay, for that is Y bar 1 minus Y bar 2. Okay, when I subtract that, of course, the point estimate is actually 1,300. Okay, now The other time I told you that situation where this guy is a random variable. Of course, the expectation of that, because there's going to be several of that. The expectation is actually going to be the true mean difference. And we're also going to consider computing the variance of the difference of means. The variance is actually what you see inside the square roots here. Okay. And of course, the standard deviation is just going to be the square root of that. Okay. But I need you to pay attention to what you see inside the square root. Now, inside the square root, you can see sigma 1 square, sigma 2 square, right? Those are population variances, population. The sigma 1 square is population variance for the first population, and sigma 2 square is the population variance for the second. The population variance can only be obtained if I've studied all tiles. But you know what? On Friday, I was able to prove that expected value of a sample variance will give us a population variance. And because of that, we can actually replace the population variance with a sample variance. Okay. And that is the reason why you actually seeing x1 squared, s2 squared. Those are sample variances now. Now we said we want to place an error bound, error, two standard deviation. Take a look at that now. Okay, because they say two error bound. The two error bound imply two multiply by the standard deviation of the estimator under investigation. Okay, the standard deviation of the estimator here is actually square root of that. So two multiply by that, all what I'm just going to do is to plug in the values. And when I plug in the values, okay, I got this guy now. Okay, now if you take a look at that guy now, the error of estimation itself, okay, is this guy. Okay, the error of estimation is actually going to be the difference between the point estimator minus the parameter. The point estimator is mu cap 1 minus mu cap 2. That's a point estimation, the point estimation of the difference. Why the other one, mu1 minus mu2 is the population parameter of the difference. So if you take a look at that, okay, now I want to have a conclusion now. Now, before having conclusion, you know what I'm going to do? What is the meaning of that? The very first 1,300 here is the difference that we got from the point estimate, when you have the y bar 1 minus y bar 2, and 368.8 is is that guy that we got for the two standard error bound. The two standard error bound. Then we're going to write plus or minus, okay? So 1,300 plus or minus. When you take a look at this guy, oh my God, this guy is more or less looking like a margin of error, like a margin of error. Okay, a margin of error is different from standard error. The standard error is just this guy. Do you see that guy? So multiply by 2 because we're placing a 2 bound. Okay, at times in statistical analysis, it may not be true. It may actually be a z-score, a quantifier that we need to figure out. But right now we're direct. Okay, so place it 2 bound. Now, when I subtract and I add, I'm actually going to have that. So what I'm actually going to say, we can estimate, okay, the difference in mean miles to weigh out to be 1,300. That is it different. And we expect the error of estimation to be less than this within a probability of 0.95. Why do I say within a probability of 0.95? Because I'm using empirical rule. Why am I using empirical rule? Because the sample size is greater than 30. Sample size is 100. Central limit theorem apply. When central limit theorem apply, that will facilitate normality. And when you're working with the normality, you're working with the empirical rule. So two error bound is 95%. You remember under empirical rule, one bound is actually going to be 68%, and three bound will be 99.75%. I want to go into today's material, today's work, okay? But for us to be able to prepare our ground for interval estimation, you need to, I put this example here for you to actually, you can take a look at this, okay? This still under a point estimation, okay? Using a rod of length, you lay out a square plot whose length of each side is mu. Thus, the area of the plot will be mu squared, okay? The area of the plot will be mu squared, okay? You know, you're talking about area, depending if you're having a square, right? That's going to be length, the width and the length, they're going to be equal, right? Okay, now, based on n independent measurement, x1 up to xn of the length, estimate mu squared. You know, here we're not estimating mu, but we're estimating mu squared, which is going to be the area. Okay, now, assuming that each SI has a mean mu and a variance sigma squared, now show that x bar square is not an unbiased estimator of mu squared. I need you to pay attention now, okay? You know, expected value of x bar, okay, or, you know, we'll be using whether x or y. Expected value of y bar is mu, but expected value of y bar square is not mu squared. Take a look at that. It's not. Expected value of y bar is mu, but expected value of y bar square is not mu squared. And I want to show why it is not, okay? Show that s bar squared is not an unbiased estimator. If you want to show that s bar square is not, what we're trying to tell the world is that expected value of x bar squared is not the same thing as mu squared. Okay, now let us now see. And after that, for what value of k is the estimate unbiased for mu squared? Okay, now let's get started. You know, for us, I need you to take a look at this guy. You know, we're focusing on we're focusing on expected value of s bar square, right? We want to see whether it's going to give us mu square or not. Now, what we actually need to remember from what you've done before, okay, from what you've done before, okay, variance of x bar is expected value of s bar squared minus expected value of x bar all squared, okay? I tell you know that. Now, I want to find this guy. This is going to be expected value of x bar squared equal variance of x bar plus this, right? That was how you got this guy right circled, okay? Now, what is the variance of x is sigma squared. What is the variance of x bar? Sigma squared over n. Now, and we all know what is the expected value of x bar, okay? Expected value of x bar is mu, right? Now, then what is the expected value of x bar or squared? If this guy is mu, then this guy is mu squared, right? That was how you got this guy here. Does that make sense? Now, when you take a look at that, is that unbiased? No. For it to be unbiased, we should only have a mu squared. But what are we having now? We're having a sigma squared over n plus mu squared. That is why it is biased. Does that make sense? Okay, now, and if I want to know whether, if I want to calculate the bias, okay, if I want to calculate the bias, the difference between this guy and mu square is going to give you a sigma square over n. What is going to happen here if you make an attempt, like if you want to use X bar squared to estimate mu squared, okay, because this is showing that it is going to bias. What is the implication of that? The implication is that it will overestimate. Don't forget, you are adding something more to that. That is overestimation. Does that make sense? But when the bias is positive, that is overestimation. When bias is negative, that is underestimation. Does that make sense? Whether overestimation or underestimation, that's a problem. Okay, now we're done with that. Done with that now. We got to move right now. Now, another thing we want to do, you were given this particular function because we know that X bar squared is going to be a bias estimate of mu squared. And we can at times suggest a linear combination of X bar squared. Now here, it's okay. What if I remove KS squared, where S squared is the sample variance and K is unknown? Okay. Now I can decide to figure out what the K is going to be when I'm assuming that this is going to be unbiased. Please, I need you to pay attention. Now, do you know that, right? When I use expectation to multiply this, when I use expectation, it's going to grab that, the constant is going to come out. Okay? Can you see that, right? Okay, now, what is the expected value of X bar squared? That was what we got here. And that is what I'm actually plugging in here. You see that? Okay. Now, K, what is the expected value of sample variance? Sigma squared. We proved that last week. Do you see what we have now? Now take a look at this. Give me 1 second. Now, if you take a look at all this, okay, what do we want? We want a situation. We want to determine the values of K. Please, I need you to focus the ball. This is good. This is algebra. What do we actually want? We want mu squared. If you don't want if you want only mu squared, then what is going to happen? Okay, let me do this. If I only want mu squared, what is going to happen to that? I will equate that to 0. When I equate that to 0, then I will be able to find K. Because they want you to figure out what is going to be the values of K for this guy. What is going to be the values of K for this expression to be unbiased. So after getting to this side, we are actually looking for this, right? If you're going to equate that to 0, then you solve for K. Okay? When you solve for K, your K is going to be 1 over n. So which means when K equal to 1 over n, then this is what we are expecting. So the estimator now is what you have in the parentheses. Does that make sense? Okay. Now, take a look at this guy. Just another example. When you are working with two population, and of course we've had situation where we combine variances that we call pooled variances. Has anybody heard about pooled variances before? Or we put our variances? Okay, take a look at this. Suppose fertilizer 1 has a mean yield per acre of mu1 with the variance sigma squared, whereas the expected yield for fertilizer 2 is mu2 with the same variance sigma squared. Okay, we pull variances in statistical analysis when we assume that the population variances are the same. When you are conducting a two sample t-test, and we get assumption that population variances are the same, then we pool the variances. Okay, so now Therefore, if you take a look at this guy, that pool variance is an estimator. How are we going? How can we show that this estimator is going to be unbiased? What do I mean by showing that it's going to be unbiased? We want a situation whereby the expected value of that estimator must be sigma squared. Okay. Then if I want to do that, I'm going to introduce expectation to both sides. That's what I'm doing here. Take a look at that, expectation to both sides. Now, the only random variable here is the two sample variances. The expectation is going to grab them. And of course, we've proved in this class, expected value of sample variance is going to be a population variance. So if expected value of sample variance equal to this, then expected value of this is going to be this, then expected value of this is going to be that. And don't forget, we're told that this equal to this, then equal to sigma squared. We've already been told that the two population variances are going to be the same. So that was why you see sigma squared, because sigma 1 square equal to sigma 2 square. That was the assumption before using a pool variance. And at the end of the day, when you simplify this guy, you're actually going to have a sigma squared. And that's actually validates the pool variance estimator that we use in statistical analysis. I want to go to interval estimator now. The interval estimator is going to be so easy. With the interval estimator, why do we need interval estimator in statistical analysis? We need interval estimator in statistical analysis because there is possibility, according to the classical approach of probability, that a point estimate value could be wrong or right. I'm going to say that again. A point estimate could be wrong or right. Even if you have done everything that you're supposed to do, it could be wrong or right. To be at the safer side, we normally consider interval estimator, because why do we think interval estimator is actually going to be safe? Because that will give us opportunity to also consider what I call the margin of error to the right, error to the left. And of course, in the interval, you can be rest assured, we got a guarantee that the true value of the parameter will lies in the interval with the associated degree of confidence. And of course, describing estimator using interval, we enable us to see how sample, your observation of the sample reflects the overall view of the population. Okay, now let me tell you this. If a point estimator is a random variable, then an interval estimator is also a random variable. Now, an interval estimator is a random interval because the point estimator itself is a random variable. Okay. Now, if we want to calculate, okay, we're actually going to have two bounds of the estimator now. We're going to have a lower bound. We're going to have an upper bound. And let me tell you this. I've walked you through some property of a good point estimator. We're still going to do some of them. We only consider whether it's unbiased or not. We consider the variances. Okay. But right now, we also have a kind of way to assess whether an interval estimator is good or not. Let's see. Okay, a good interval estimator, a good one. Okay, a good one. Okay, of a parameter theta should be one. There should be high probability that the true value is a parameter lies between the lower bound and the upper bound. should be high probability for that. And number two, we should also have a high probability that the range, what I mean by range, right? Okay, when I subtract the lower bound from the upper bound, the range should be small. What do I mean by small? It should be very, very narrow. It shouldn't be very wide. When it is wide, there's a problem. Does that make sense? Okay, so these are the property of a good interval estimator. Any question? Okay, now let me tell you this. In interval estimator, we use what we also call interval estimator a confidence interval. Confidence interval. Okay. Now, in the interval estimator, let me tell you that at time we could consider two-sided. We can consider lower-sided. Maybe we only consider the one part of the interval, or we can also consider the upper-sided. I need to take a look at this guy now. That's a two-sided confidence interval. Okay. Now, we also have one-sided, and the one-sided can be in two ways. He said I'm considering if you take a look at this, the upper endpoint, the upper confidence limit, or the lower confidence limit. Take a look at that. Okay. Now, and I told you the other time, and we're also going to have what we call confidence coefficients. The confidence, whenever you are describing something in an interval, because mathematician told us when you are describing something with an interval, there's going to be error. And that is why we need to have some degree of confidence. Okay, the confidence level, the confidence coefficient now is actually going to be the complement of the level of significance. Has anybody heard about level of significance, alpha? Like we talk about, like if the level of significance is 5%, level of confidence is 95%. The level of significance is level of statistical error. If I say 5%, if I say my level of a statistical error is 5%, it means in my research I'm only going to mislead people 5 out of 10. Okay, 5 out of 10. That's okay. Well, even in research, we mislead. Our research is not perfect because model is not the same as reality. Okay, so for two-sided confidence interval, so the probability that the random confidence that we enclose theta, we want that very probability to be very high. Okay, so that is what we're talking about. This is for two-sided. Okay, that is for two-sided, right? That's for two-sided. Then we can also consider the one-sided. We can figure out what is the probability for the lower bound and the upper confidence limit. Okay, I'm going to go into an example now. Okay, suppose that we obtain a single observation y from an exponential distribution with a mean theta. So use y to form a confidence interval for theta with a confidence coefficient is 0.9. The confidence coefficient is 0.9. That is like 90% confidence. 90% confidence actually means 10% level of statistical significance that we call level of error. Okay, now suppose the confidence interval is of the form. Take a look at this. Suppose it's of the form y over b, comma y over a. We are, 0 less than a, less than b. Of course, b is more or less like the upper and the a is the lower. They are constant, okay? And that constant a and b do not depend on theta. Okay, can we have a way to find the values of what a and b is actually going to be? Now, for you to find the values of a and b, you need to, for us, be given the level of confidence. The level of confidence is 0.9. So now what I want to figure out, what is the probability of the true value of a parameter is going to lie between that and that. Oh my God, do you remember what we did on that proportion? where, okay, oh, y is a Bernoulli random variable, and you sum y become binomial, and you want to figure out a p-cap, right? When you want to figure out a p-cap, that's going to be y divided by n, right? Okay, it could be something of that nature. So take a look at this. But I need you to pay attention to the underlying distribution. You were told it's exponential and the mean is theta. Okay, if the mean is theta for exponential, the variance is going to be theta squared. Now, don't forget, I want to find this probability. If I want to find this probability, that's going to be easy. I'm going to make use of the underlying probability distribution. Take a look at this. Okay, now, you know, how do I have, you know, initially I actually have this guy. Okay, I have y over b. Okay, I can change that mathematically into a theta, y lie between a theta and less than b theta. So which means this guy here is the same mathematically as this guy here. Of course, why do you think I'm moving? Okay, because here this is only going to tell me the probability that theta, where theta is going to be a random variable, but theta can never be a random variable. A population parameter is constant, doesn't vary. You know what varies? What varies is y or the estimator. Does that make sense? And that is the reason why we actually need to have a way or to have a mathematical manipulation in such a way you're actually going to have y in the middle. Because when you have y in the middle, you'll be able to make use of a distribution for y. The distribution for y is the exponential. Take a look at that now. I want to find the probability of y lie between a theta and b theta. It's actually going to go, I must be ready to perform an antiderivative because the f of y, which is the exponential distribution, is a continuous probability distribution. Now, take a look at this guy now. That is the probability distribution of exponential because you've been told. Okay, look at the example. Suppose that we obtain a single observation y from an exponential distribution. You already been told. Okay, now we got this guy now. By the time you plug that in, you're actually going to get this guy. Okay, now when you get that guy, don't forget, you're going to equate to 0.9. But they gave you a 0.9 to be level of confidence. Okay, now I need you to pay attention to what you have over there. Okay, the total area under a curve has to be equal to 1. If the level of confidence is 0.9, do you see I'm referring to this guy here? This is a density curve of an exponential distribution. Now, when you take a look at the shaded red side, that is 0.9. That is then 0.9, what are we left with? What we're left with is just going to be 10% that you can divide into 2 equal parts. That's why you see the blue part is 0.05, the other blue part is 0.05. Take a look at that. And with that, do you know that we can have absorption where we set this to this? Because the difference between this and this is 0.9, right? If the difference between that and that is 0.9, and as you can see here, if I partition the entire cycle into 2, I'm actually going to have 0.95 and 0.5. Into 3 is going to be 0.05, 0.9, 0.05, but into 2. Okay, it's going to be 0.95, 0.05. So I can let this guy to be 0.95 and let this guy to be 0.05. When I do that, I'm only going to solve this mathematically now into this in log, and that will give me opportunity to be able to get A and B. Okay, now this is positive, right? I will need to set this guy to the larger part. That was why I set it to 0.95. Does that make sense? Because this guy, this is positive is 0.9. Okay, so that was why we did that. So if you take a look at this now, we succeeded in finding A and B. After finding A and B, we still need to go back and plug in. I'm going to plug in back here. So when I plug that A and B back, okay, oh my God, take a look at this guy now. What have I done? I've already plugged in A and B that I got. You see that? I've plugged in A and B that I got. And I'm actually going to say in interpretation, we are 90%, so the 90% confidence for theta is that, okay? So the probability that theta is within, when you say 90% confident, we're trying to say the probability that theta is actually going to be within is 90%. And don't forget the other time, if you want to judge how good an interval estimator, the probability that is going to be within should be very, very high. Okay, so take a look at that. Okay, suppose that in a realized experiment, y is observed to be 1. Don't forget, the other time, they told you here. Suppose we obtain a single observation. Single observation means y equal to 1. Does that make sense? Now, and that was why, that's what we're trying to say here. Okay, suppose that in a realized experiment, y is observed to be 1. Can we conclude that the probability of theta b between that and that is 90%? Okay, and it is no. Why no? Because that is for sample size of 1. Sample size of 1 is dangerous. Sample size of 1 is more or less like making y, to behave so crazy. Like there's nothing like a randomness in it. Does that make sense? And that is why we normally want a situation where, in fact, we normally want a very large sample size. That's why we have the law of large number that will ensure the convergence of a point estimator, okay, to the population parameter. Okay, so no, because theta is a fixed constant. So thus, either theta is within or it is not, which is a certain or impossible event. So now let me tell you this. It's 50-50. It can be in it or not. When something is 50-50, that probability is not high. Does that make sense? It is not as if it can't be within the interval, but the probability to guarantee is 50-50. It can be 1 or 0. That is too dicey. But we want a situation where we can be sure like 90-something%. Okay? Now, we could simply say observe 90% confident interval for theta is that we are 90% confident. So the way we're normally going to say, we're going to say, oh, we are 90%, depending on the level of confidence given. They give you 95, oh, we're 95% confident. Oh, we are 90% confident. Okay, so that is that. Now I'm quickly going to move to another example. Now this time around, the other time we find A and B, right? But this time around, maybe they are not interested in two-sided. Please, I need you to pay attention. Maybe they are only interested in one-sided. Okay. Now, suppose that we take a sample of size n equal to 1 from a uniform distribution, a different distribution now, defined on the interval 0, theta, where theta is unknown. Okay. Now, find the 95% lower confidence bound for theta. 90% lower. Okay. You see that? So find the 90% lower confidence bound for theta. Now, suppose it is in this form, y over a, comma, infinity, then we only need to find just a constant a. When we're dealing with the two-sided, we find a and b. But for this guy now, it's going to be a. For the other one, it's going to be b only. Okay, now, when we want to do this, we need to put into consideration the probability density function of uniform distribution is 1 over theta. What you've done in 4101, uniform is 1 over b minus a. But here, a is 0, b is theta. So that was why you have 1 over theta. Now, what do you want to find now? You want to find this guy. You want to find the probability of y over a less or equal to theta equal to 0.95. Why do we say equal to 0.95? Because we actually want to find 95% lower confidence bound for theta. Now, when you have this guy, now we're gonna make it y. We're focusing on y. Don't forget, we're focusing on the random variable. Because when you are focusing on the random variable, that will enable you to use the probability distribution for the random variable. Okay, don't forget we are working with the f of y equal to that. So mathematically speaking, this guy can be written as this. Okay, it can be the probability of y less or equal to a theta. Okay, and when you take a look at the other hand here, okay, we can actually partition the entire stuff into two, 0.95. And why do we have 1/theta? Why do we have that? That's a uniform. Like it's going to be the same. It's going to be 1/theta for whatever values of theta, for a theta. Okay. You don't forget, you want to find the probability of y less or equal to a theta. Okay. For whatever values of that, you're actually going to have 1/theta, and the confidence is 0.95. And let me tell you, which can be partitioned into two. Okay, we can partition it, can be 1 or a, and I gave a condition, but let me quickly move so that you'll be able to. Now from based on this is a special situation. Uniform is a special situation. A is always going to be what that particular value. Okay, just a equal to 0.95, because that's a unique situation. We're talking about uniform. A is always going to be equal to the level of confidence given. Okay. Now, the conclusion now is going to be y over, we've plugged in that A now. It's a 95% confidence for theta. Okay. Which means y over 0.95 is a 95% lower. You have to emphasize lower. Okay. Confidence bound for theta with 95% confidence, theta is larger than y. So, this is like the minimum. Okay, it's going to be larger than that, but it's going to be less than infinity. Okay, so take a look at that. Now, if you take a look at what I'm trying to show here, okay, if we assume a true value to be 0.5 by 95% confidence means out of 100 intervals, the true value will only lie within just 95 intervals. It's not going to, so which means that if I have 10, okay, if I have 10, it's not going to lie in all of them. So when you take a look at all this, there are some, okay, that is 0.5. Take a look at the first one. Take a look at this guy here. You see this guy, right? If you count how many, you can count the numbers of that the true value doesn't actually lies. Okay, this is to tell you by confidence interval is not going to contain all the the parameter value. So that is why we call that that. Lastly, and this is interpretation of what I just showed. If the same procedure was used many times means I go into population, I compute 100 intervals. If I'm using 95% confidence, the true value will only lies in 95 of the intervals. If I'm using 90, it's only going to lie in 90. So I said each individual interval will either contain or fail to contain the true values of P, but the percentage of all intervals that capture P will be very close to 95%. That is on the long run. Okay, that's what we mean. Okay, that is going to be the end of the lecture for today. Is there any question? Any question before I go today? Any question? Okay, make sure you all stay safe and have a beautiful day. Bye for now, everyone.